Hello. Okay. So, as Jason said last year, I did this talk. Did anyone see that? Show of hands. Okay, a few of you. So this is a continuation from last year. I will touch on some of the same topics as last year in a couple of areas for those of you who weren't here. But I'm going to talk a little bit more about where we've gone since we did this talk last year. Anyway, so just a bit about me. I've been in observability for now 10 years. Back in my last company, Dataloop.io, was a cloud monitoring company. Back in 2013, we sold out in 2019, and then a year later I joined Netflix, who used to be one of our largest customers, and invited me to come and head up the telemetry engineering team at Netflix. So I've been there for 4 years now. And then for those of you who just want a bit of a context on what we do in observability engineering at Netflix, we collect a lot of data, and we ingest that, we store it. Everything is built in-house, everything is bespoke. I'll talk about why later. And then we have a bunch of products which we call exploration and troubleshooting, which is like metrics explorers, logs UIs, all those kind of things. And then we have a whole load of products for monitoring, alerting, and helping users figure out what's going on with their systems. So what are the challenges that we've had pretty much that led us to the paths that we're taking and the things I'm going to be talking about? So as you all know, we're a video on demand streaming company. We started streaming about just over 17 years ago now. And in the last 10 years, my team specifically basically built probably the best observability solution at scale for a large scale video on demand streaming company. But as some of you know, we've expanded into a whole load of other areas in the last 2-3 years. And that's put a lot of stress on the team to basically adapt our platform for lots of different use cases. So things like gaming, they have a bunch of different observability requirements than you would have on streaming. Ads, different requirements, different users, they want to look at different metrics, business metrics. Live, low latency. We need to be able to show dashboards very, very quickly, very, very low latency, so when people are doing live broadcasts, they can respond to incidents very quickly. And on top of that, like every other company in the industry, we're also doing a lot of AI and a lot of machine learning and running batch jobs, Spark jobs, all that kind of stuff, and we need observability for that too. So we've basically gone from having to support one business into multiple business units, and that's all happened in the last 2-3 years. And we're a small team of 30 people. On top of that, as Notorious B.I.G. said back in the 90s, more data, more problems. And boy, do we have data. We have still consistently about 17 billion metrics a day coming into our metric system. On Insight logs, we've actually doubled since I last spoke to you. So we're now doing 3 petabytes of logs a day, and that's still going up. That number is not ending there. And then tracing, same thing, over double. We went from 70 billion traces to 160 billion traces in the last year. And I'm going to talk about a few use cases that have kind of driven that growth in the last year. So you can see we're operating at scale and we're growing very fast. And then, of course, like every developer out there, everyone wants more cardinality, and we're constantly being pushed to add more tags, more dimensions to all of our data, being able to index it, search on them, all that kind of stuff, so developers can get more insights out of their observability data. The next problem that we also have to deal with, which I guess is familiar to any large company, is we have a lot of engineers, about 3,500 engineers, which is actually quite small considering the scale of our service. We run pretty lean, but we have some phenomenal engineers. And one of the things we've been guilty of, I know some vendors are also kind of addressing this issue, is discoverability. Like, flat lists of dashboards where you have to style your own dashboards doesn't really scale when you get to 3,500 users. Hundreds of thousands of alert rules where you have, pretty much just have a flat list of alert rules. We solved that a couple of years ago, but, essentially, we have to organize our information in a better way so we can help our users find which out of the thousands of microservices they care about, they can find very easily with the dashboards, the alerts, and everything they care about. And on top of that, we have to scale the best practices. Like, what should a Java engineer be looking at? What should a Python engineer be looking at? Those kind of things need to be scaled across the company too. So we have a lot of user scale problems as well, which we need to address. And then on top of that, we also have to care about cost because we are a very fiscally responsible company. We do care about our margins. If you look at any public report for Netflix, you'll see we've got some pretty phenomenal margins. We have very good cash flow. And so the business does not want us to basically just, exponentially grow our observability costs as our data goes up. So I'm pretty sure they would have freaked out if we doubled our observability costs in the last year in response to those logs and tracing. So this is actually what's kind of driven us to basically build everything in-house, like a lot of our peers at our scale. because if you look at this list, I haven't named the vendors, but essentially, we are still a fraction of the cost it would cost us to send this data to an outside vendor. And we speak to them regularly and get a good idea of cost and stuff. And the main reason for that is just basically shipping this data out of AWS. First of all, that would cost a lot of data, but then even just basically having to pay margins on someone else's AWS costs when we have pretty good, discounts for AWS at our scale, that just also adds another layer of cost and all the other things as well. So we have to worry about that. So in summary, we've got to handle more use cases, we've got to handle more data, more cardinality, we've got to handle better discoverability across our 3,500 users, plus disseminate those best practices across the organization. And we have to make sure that we keep decent margins for the business without exploding all our AWS bills with observability. So I'm going to talk a bit about the solutions here. So the first piece of the thing that we did last year in response to some of these challenges is we had to partition our data. We had a one-size-fits-all kind of stack that was, again, like the best for video on demand streaming observability. But with all these new use cases, they have different requirements. We had to basically partition our data in a way that we can scale to what's going to eventually be hundreds and thousands of namespaces across the business as we kind of scale out. So we do that by namespaces. I'll talk about that in a sec. We had to basically add low latency streaming UIs. We had to do that, one, for the observability data lake, which I spoke about last year, but also we had to do that for live. We had to do a lot of work to make sure that the latency between when metrics came in and when you could see them on a dashboard or an alert was very, very low. So in a live event, we can respond very quickly. We also had to think about discoverability. And so we actually have an internal service catalog. We call it Netflix Console. And we've basically had to build a bunch of stuff around that. I'll talk about that in a sec as well. And then finally, the kind of crunch of this talk is basically the new storage solution on S3, which we call the Observability Data Lake, or shorthand ODL. So first things first, namespaces. So what we've essentially done is basically build a service called Namespace. It allows us to basically store the configuration for a namespace, which basically means you can configure the schemas, the indexes, you can configure the retention periods. All of this stuff is configured as code, so it's like a multi-tenanted kind of service. And the reason we do that is because eventually we imagine right now we only have maybe less than 10 namespaces. But it allows us to basically configure the data requirements for different use cases. So for example, batch users were doing Spark jobs and all those kind of things. They want to have 6 months of data retention, which at streaming scale would be prohibitively expensive. But for their scale, still expensive, but we can do that for 6 months. And so what we basically built is a service where we put that configuration. What do you want for your retention period? What do you want for your schemas? What do you want for your indexes? How do you want to partition the data? And this basically allows us to automatically deploy out new kind of clusters, and namespaces could be new tables inside an existing database, and essentially configure that, manage that configuration automatically through code, which is how we're going to scale this out to thousands of different namespaces. And that allows us to support all the increasing number of use cases that we have across the company. We've done a lot of work to basically support low latency streaming UIs. So last year I talked in depth around our streaming API called LWC. We call that internally. If you didn't see my talk last year, watch the video online, and that will go into detail here. But essentially, we were having latencies on some of our metrics for like 4 or 5 minutes, which during a live event isn't acceptable. So in the last few months, we basically got that down to less than 10 seconds for any metric that's coming in those 17 billion metrics that we kind of store. And that basically allows us to do very live, responsive dashboards and alerts for our users during a live events. We also have this year rolling out a service catalog called Netflix Console. So essentially, this allows me as a team to see all the services I own across the company, and then basically, it basically solves the discovery problem. But the thing that the service catalog also adds, it adds metadata about all these services. Who owns it? What's the GitHub repo? What type of service is it? Is it a Java service or Python service? Is it a Spark job? Is it a microservice? All these kind of things basically are kind of stored as metadata against each service. And so this actually gives us an opportunity to build curated experiences that can be embedded inside the experience for the service catalog. So if I go to my app and it's a Java app, we can provide a curated experience for Java apps with like the dashboards they need to look at, the alerts they need to have, and all the other observability things that they care about for a Java team. We're still not quite there on that kind of part yet, but that's kind of the vision of where we're going with the service catalog. And so we're actually building all our new UIs into the service catalog to help with this discovery problem. And then the bit I just talked about, like how do we essentially allow what we call local central teams, so that's like the Java team, the Node.js team, the core team, which is our SRE team, how do we let them essentially build curated experiences for their different user bases? So all the Java developers get best practices, disseminated for the type of dashboards they need, the type of alerts they need, and et cetera, et cetera. And so we call them managed packs. We actually roll them out with alerts. We call them managed alert packs for the first version. But essentially, what we're building is tooling for these local central teams to essentially take ownership. This is also how we scale our 30 people in observability out to the rest of the organization for all these different use cases. We're giving them the tooling to essentially create these created experiences, monitor them, see who's using them, what their kind of response has been. Alert noise is an important one. We want to make sure we're not spamming all our users with crappy alerts and stuff, so they can kind of monitor that and allow them to iterate it and then manage that lifecycle. How do you push out a new change? So how do you depreciate an alert that we've decided is no longer relevant? So all that kind of lifecycles tooling we're actually building at the moment, so that we can start basically pushing these kind of curated experiences for all the different user groups out in Netflix and all these different use cases out to local central teams that can then manage it for their respective user bases. And that's all going to the service console that I was talking about before. And then last but not least, how do we control our costs? So last year I talked about this pretty in detail, the observability data lake. So essentially, we want to basically put all of our data into the lowest cost storage solution, which for us is S3. And we want to basically be able to provide the same kind of query performance that you get from, maybe some SSD solutions or hot tier solutions out there, which are very expensive at our scale. And that's a very hard computer science problem to solve. I go a lot into the way we do that last year. I'm going to touch on it in this talk, but I'm going to basically go into kind of how we are basically looking at building this inside Netflix. And so in the observability data lake, we want to essentially put all of our data in it for any data set, whether it's metrics, logs, traces, all of that stuff. We just want to put it into one solution. Because right now we have different solutions for metrics, different solution for logs, and a different solution for traces. We now just want to put this into one platform where just through configuration, we can optimize it for those different data sets for metrics, logs, and traces, and eventually profiles and RUM and NetFlow monitoring and all the other data sets that we want to add in the future. But we had to start somewhere. So last year, when I did my talk, we did a demo of tracing. It was basically a GraphQL experience. I showed a demo of how we were able to essentially do queries on S3 in less than a second. That was basically a small proof of concept, working at a good scale, but not the scale that we are today. And so we decided to kind of stick with tracing when we started this project last year. So essentially, our current storage for tracing is based on Cassandra and Elastic. It's worked pretty well up for the last few years. The problem is it doesn't have any aggregation capabilities. So we're not able to do those kind of aggregation queries and graphs of all your spans and what the trend of your latencies are on your traces and stuff like that. We couldn't do that on top of Cassandra Elastic without adding a prohibitive amount of cost and complexity to that solution. We're hitting the scale limits of it already. And on top of that, it's very expensive. And in terms of scale, it's something that's already running at scale. So we've got 160 billion traces. That's about 1 trillion spans a day, 369 terabytes of data a day ingested. We're growing very fast in tracing. So for all these reasons, we were like, this is an obvious candidate for us to start with before we get to metrics, logs, and the other data types that we want to. So let's prove it on tracing, and then we can move to those other data types once we've got it proven in one domain. We also have a lot of tracing. I would actually say we're reaching a tipping point at Netflix where tracing has become this thing which people go to sometimes, to now people are relying on it more and more, and we have more use cases being built on top of tracing, which I'm going to talk about now. The trade-off with this one versus metrics and logs was it is the hardest data set to partition. Like, how do you partition a trace that touches hundreds of different microservices? With logs, you can typically partition it by service, because most users are basically trying to just search for a set of logs in that service. So you reduce the search area by partitioning it per service. For metrics, there's other ways of partitioning it. Tracing, how do you partition it? I mean, a trace goes across multiple services. We actually ended up using a technique where we look at the call path of the shape of a trace, the call path of a trace, and we use that as a partitioning. But I have to say it's not perfect because we have a lot of requests that go in a very similar direction. And so we end up with a huge data set that's one partition and then smaller data sets for other less commonly used trace paths in Netflix. So, so it's not perfect, but it still allows us to do partitioning. So that was the trade-off. This was the hardest one to partition. But these are the kind of new use cases that we're essentially seeing that are driving that number up by 200% this year. So this year, we've essentially been working closely with our consumer engineering team to enable end-to-end tracing. So right now, all our tracing is pretty much started from the API proxy, which is where all the TVs and phones and everything connect to kind of stuff. So that essentially an engineer can see what's going on once they hit AWS and what's happening with all the different services they're talking to. Now, we're starting the tracing from the client devices. And that's adding billions and billions of spans. Obviously, for every single request, we're now adding much more spans into our data set. So that's contributed significantly to our growth in the last year as well. The other thing as well, I showed a demo. This is actually screenshots from a demo. We're being asked to, we're moving as a company to GraphQL. Our GraphQL users do not have enough observability. They want to be able to see how their operations are performing. They want to see which services their operations are calling and find where they can reduce latency for those different calls. So obviously tracing is a perfect candidate for that. So we're basically building a GraphQL observability experience for those users based on ODL, because that's the only way we could basically build these kind of capabilities at scale for the GraphQL users. So that's another use case that's really pushing the limits of our tracing system. This one is actually the reason why our logs mainly have doubled in the last year. It's basically Spark jobs. So we've been doing, like a lot of tech companies, machine learning, AI for a number of years. And we have lots and lots of Spark jobs running constantly on cron jobs, daily jobs, ad hoc jobs, all that kind of stuff, thousands and thousands of jobs every day. And they produce petabytes of logs, and they produce a lot of information and metrics. Because of the way jobs run, traces are actually perfect for batch observability, because they basically show you like how a job kicked off, and then here's the sub-jobs that kicked off, here's how long they took in terms of spans. So we're using tracing for this, but it's generating a lot of data, not just in terms of logs that we collect that are linked to those traces, but also the traces themselves. And this is actually the first part of the aggregation capabilities on top of logs, because users do not want to look at an individual job per se. They want to see trends over time. Is my job getting slower? Is my job, if it's getting slower, which part of the job is actually making it get slower? So those aggregation capabilities are now becoming front and center for us in terms of tracing. And then the last thing, actually, this is actually a really cool use case that we've been engaged with in the last few months. So our data science team are doing, like most web scale companies, we're doing A/B tests. We're testing different features and stuff across the world. One of the data points they didn't have is, how do you know how much a feature is going to cost when you roll it out to all of the users at Netflix, which at our scale can be pretty expensive. So in this example here, we have an A/B test. Option B obviously was much more successful, 25%, but it cost $2 million extra in additional infrastructure spend to support that feature versus the option A, which was only $100K in additional infrastructure cost. So with trace data, we're able to actually help that team do estimations and reports that allow their product management teams to make more informed decisions. Like, yes, this feature will have an uplift in X, but it's going to cost you several more million to roll this out across all the users. So now they can make a more, is it worth several more million for us to do that kind of stuff? So it's been used for this type of use case as well. Now, as I spoke about last year, trying to do, we want to store things at scale and the cheapest possible storage solution. So S3 is obviously the cheapest one, at least for us, to kind of run on. The trade-off there is latency, and so this table basically describes it all. If we did it in memory, we can do it super fast. We do it on S3, we're going to hundreds of milliseconds just to start pulling off files and reading them. So that's the thing we have to solve for. And last year I talked about my own, I think everyone's been announcing theorems today. This is my theorem, the CSL theorem. I put a trademark on it because some vendors after last year started putting it in their slide decks. So you're welcome to do that, just reference back to me. Essentially, the hard problem of observability is we want low cost, we want large scale, and we want low latency. And trying to solve for those three things has always been a massive challenge in our industry. So that's what we're trying to do with the observability data lake. And we think we basically, we've basically, at the moment, are proving that we can do it if we just think differently about how we do queries and stuff like that. So this is the architecture that I showed last year. It hasn't actually changed that much from when we first designed it. We're actually running this now in production with all our trace data. So, but I think the key thing for basically reducing query latency is, first of all, you need an index. I'll talk about that in a sec. The index is actually the key thing to help reduce that amount of data that you want to kind of query, because if you have to pull a lot of data from S3, obviously that's going to take longer to query. So if you're having to, if in a petabyte of data you have to scan half a petabyte of data just to get the graph back, obviously that's not going to be very fast. So the index really helps us focus in on the actual files and data in those files that we need, and reduces the search area. The second thing is you need to basically have fan-out compute. So we use Amazon Lambda for that, functions as a service. Because some queries will come in and we can just handle them on our query service, but a lot of queries will come in and we just need to process those files as quickly as possible in parallel. We're not the first people to do this. Some other vendors have actually spoken about doing this in the past, but as you can see, we're doing it at quite a large scale and it's working. And we store all the data on S3 in Parquet files, which also gives us a compression. And essentially, this is basically the architecture. And actually, what's quite unique about this solution versus other vendors that we've seen out there, we don't wait for the whole query to finish, because some queries will naturally just take 10, 20 seconds. We can't fight the laws of physics. But what we do is we stream all our queries so that in the UI, you will start actually seeing the first set of results in a table that works phenomenally well. First results appear almost instantly, and then we stream the rest of the results afterwards. For graphs, it looks a bit more different. You're seeing the graphs kind of streaming in that way. But we think that works from a usability point of view. And I think we'd rather have that type of experience versus spinning logo, where people are just waiting just to see if their query was even correct, or even we're showing them what they wanted to show before they type in another query. So we're really looking for that responsiveness. So, okay, I didn't realize it took that long to get here. So in terms of the index, what I'll basically just talk about here, with indexes, you're basically trying to get a compromise between size and cardinality, capability, sorry. And so we've basically gone for a balance. We index every single field of every single span that comes into our observability data lake. And because different fields have different cardinality, different requirements, we use different indexes for every single field. This is basically the secret. This is how we basically scale an index. That's able to, for multiple types of queries, able to look up on any type of field in a span in milliseconds. So we basically have an index that essentially allows us to configure for this schema, index these fields with these indexes, and then we use those different indexes to look up the data really quickly, up to the byte level. So we actually index at the byte level in Parquet files, so we don't even have to scan the entire Parquet file to get like a row or that kind of thing. And we can also use the index for projection. So some queries don't even have to hit Parquet. We can actually, for like a duration index, if you want to see a histogram, we can go straight to the duration index and produce a histogram of all your traces just from the index. We can also do stuff like show you a list of autocomplete tags when you're typing in your query using a tree index and projecting from that. So there's a lot of, so the index is really kind of like the key to this. And this is the result so far. So you can see we're doing a lot of data. Our index is about 16% of the data. We compress it about 83%. Right now, before we've done any optimizations or anything, we're doing about 66% cheaper than our current solution on Cassandra Elastic. And in some of our queries, we're seeing up to 10x faster. On average, it's taking about 2 to 3 seconds for most of our queries to kind of go through for users. We still haven't done anything to optimize that, so we think we can get that below a second. But this is just phenomenal compared to what we were spending on Cassandra Elastic at our scale, especially. So that's what we're seeing in production. So where are we today? So we are essentially, this is our kind of strategy for how we're going to basically finish building this across Netflix. First version was make it work. We're past that stage now. It is working. It's in production. Second stage is optimize for cost and performance. That's where we are right now. We're doing a lot of changes. That's why I didn't go too much into the technical details here, because I suspect it's going to change quite radically in the next 6 months. We will do a blog for people who want to understand how we did the index and all that kind of stuff more thoroughly. And also, we're doing the first versions of ad hoc aggregation. So you saw for batch, there were some graphs there. That's using some basic ad hoc aggregations on top of the trace data. We plan to expand that with a query language and everything, so you can do aggregations on top of tracing, in real time, basically on top of S3 data. And then finally, once we've proven it for tracing, we plan to add in logs and metrics as the final part of our observability data lake. So really, I know a lot of vendors have been talking about kind of teeing off data to lots of different vendors and reducing costs and stuff. That is definitely one way to solve costs. Ideally for us, because of our scale, even that will cost us millions of dollars just to tee the data off to a different provider. We don't want to basically use a bunch of siloed solutions where we have to replicate the data in multiple places just to basically get a security monitoring solution or an AOps solution that we're interested in. But we do want to work with vendors, by the way. So our vision really is to essentially have an observability data lake where we store the data in the lowest cost feasible way and allow vendors to build solutions on top of us. I think that's really where the industry would like it to go. But the way to get there is we need a standard observability query language, which we don't have. And I know we talked to you this morning about OTel and how hard it is to get another standard on top of the other 14 standards. But essentially, we do, if we can standardize the way we do queries, we first of all solve the siloed data problem. Vendors can start focusing on solutions that actually build on top of the storage engine instead of having to build another storage engine, and then we have to send all our data over to them because they don't support the data engine we have. And then also, even if you're moving from one vendor to another, like, yes, we talked about OTel solving the instrumentation problem. The massive problem I've always seen in most companies right now is once you decide to move off a vendor, it takes months to migrate all your dashboards, alerts, everything, because you have to basically translate them to a new query language. So we believe we need a standard query language, and that's actually what we kicked off again last year with one of my colleagues, Chris Larson. In the CNCF Tag Observability group, we kicked off the Query Standardization Working Group. And what this working group is basically looking at is talking to all the vendors, we've spoken to a bunch of them already, a bunch of users and all that kind of stuff, and basically understanding what is it that a query language that can work across metrics, logs, and traces need in terms of core capabilities, core use cases, all that kind of stuff, and basically come up with a query language that could work easily across all three data sets. And so we're at the point now where, we've got some data, but we still need more help. We need to get more use cases. We need to vote on the features rubric by the end of July, and we've got a bunch of meetings that go on. So basically the call to action here is if any of you are interested in supporting this, we want this to be more a customer-led experience than a vendor-led experience like OTel, because to be fair, OTel was a bit of a kitchen sink of every vendor's requirements kind of funneled into it. So we would prefer this to be more customer-led and what we actually want as customers in terms of our query language. But if we can do this, then we can move to a world where the storage solution becomes a commodity essentially, where we don't have to essentially worry about what storage engines and what things are used, and we can start building solutions that sit on top of these storage engines and are actually more valuable to us as users. So that's really our call to action. So thank you. Okay.
All right. Do we have any questions? We've got time for a couple questions. One right in the middle.
Okay.
So I think there's this major shift of everything going to object storage, and it sounds like another thing that can allow arbitrary index types per field is an RDBMS, right? So one question I have that I didn't see in that stack with all the data is are y'all thinking about graphs as a query vector into your observability data, having the system structures interoperable coding?
So I'll just repeat the question. Are you thinking about graphs, being able to visualize this in graphs?
No, as in knowledge graphs.
Knowledge graphs, gotcha.
Yeah, I think I know what you're saying. So last year I did actually talk about that in my talk. That's probably why. So one of the first iterations of our tracing catalog, the index, was basically a graph database of here's all your cool paths, here's all your services, because one of the query types we are going to be supporting, and we can support that on the index that I just described very briefly, is most developers are coming to it not they want to see a whole bunch of traces for this request. They want to say, I know I've got service B and I've got service F. I want to see basically the latency for service B to service F, and then we have to find all the traces that match that kind of path and stuff. So that's actually another index that we actually did experiment with last year. We've used some of that stuff for the partitioning part of it. I'm not sure if we're going to continue using it in the index, but we will be supporting that use case, which is you can now filter by the shape of your trace and start seeing where all the errors and performance issues are, especially at our scale. Users do not want to see thousands of microservices in a massive trace. They want to focus it down into the piece that they're interested in.
Any other questions? Oh, got one right here. Oh.
Hey, how many namespaces and what effect did namespacing service have on your overall pipeline?
How many namespaces and what effect did it have?
So right now it's less than 10. You know, so it's still new. We built it last year and did all the design and build last year. We're starting to roll it out to different use cases and stuff like that. However, it's been designed in a way that essentially, you know, we could have a namespace per service. You know, I don't know if it will head in that direction, but essentially we expect there to be one day thousands, at least hundreds, probably thousands of these namespaces. So we've had to basically build a lot of stuff behind the scenes to make sure that we can configure these namespaces just programmatically for an API, and also programmatically create these namespaces, like, you know, so, you know, whether it's a new table, so we use a table per namespace, you know, in a database, or if it's a new cluster, you know, we want to automate all that DevOps to spin up the new cluster and manage that cluster, because we've got, like, in the team that actually do this, there's only 10 people, so that 30 people is raw observability. We only have 10 people in that team. So if they end up having to manage thousands of different namespaces, we need a way that this is fully automated.
Awesome. We're going to take the questions to the Slack just so we can catch some time back. There are, as a great reminder, actually, before I say that, let's give one last big round of applause. Great talk yet again.